Consider a non-uniform solid which is approximated by a mass distribution that's not symmetric, while each different mass I has a gravitational force acting on it. And we can find an equivalent system where all the weight is lumped at one location, so we'll call this the resultant weight. And the other condition that needs to be satisfied is that the torque is equal to the sum of the individual torque contributions from each mass. So this will become clear when you look at torques. And if you divide through by the resultant weight and then substitute for the weight, so this here is called the center of gravity, where the gravitational acceleration is non-uniformly distributed across the solid. And for the case where the solid is in a uniform gravitational field near the surface of the Earth, so in other words, Gi is constant, then we can take G out of the sum and cancel it out. And this expression here is known as the center of mass. Suppose this is an infinitely thin rod, and recall the center of mass for a discrete body. While treating this rod as a continuous body assembled of these infinitely thin elements, we can take the limit of each sum as n approaches infinity. Now if we visualize this as a differential mass element, then that's equal to the density by the volume of the element. And for this one-dimensional rod, we have a uniform area, so what we call this is lambda, or the linear density. So for this one-dimensional rod, we can write the center of mass as follows, where we're integrating over the length of the rod. But if the rod has a constant density, we can take this out of the integral and cancel it out. The center of gravity is not the same as the center of mass, and equal to the following expression, where we integrate over the weight of a solid. Now a case where these two expressions are equivalent is where you have a mass that's sufficiently smaller than a planet, whereas if you had an object that has an equivalent size to a planet, then the elements of the object that are closer to the center of the planet experience a higher force, whereas elements of the object that are further from the planet experience a lower gravitational force. And when we look at Newton's law of gravitation, you'll see that the gravitational acceleration is inversely proportional to the square of the radial distance from the planet to an element of the object that we're looking at. But in most cases, we look at objects that are in a uniform gravitational field, so as we know for a uniform bar, the center of mass is in the middle, but for a non-uniform bar, where we have stronger forces on the left in this case, the center of gravity is going to be to the left. A system of particles is connected by rigid links, and we're asked to find the horizontal center of mass relative to the orange particle, and each particle has a mass m and the rigid links are massless. So writing our expression for the center of mass, so what we do is multiply the horizontal distance to the particle relative to the orange particle as we're asked, and then multiply that by the mass of the particle. So doing the same thing to the other particles, and we multiply by 2 because we have 2 blue particles at the same distance from the orange particle. And the distance to the orange particle is obviously 0, so we ignore it. So now in the denominator, we have 4 masses, so the total mass is 4m. And I'll leave it for you to simplify this and post your answer in the comments. The density function and the length of a bar are given below. Find the center of mass. So let's take our origin at the left of the bar and draw our mass element, which is at some distance x from the origin, and has an infinitesimal width dx. So recall the integral form of the center of mass for a continuous body. So for our one-dimensional bar, we can write our differential mass as the density multiplied by the cross-sectional area of the bar, which is constant, by the thickness of the mass element. So this here is our linear density. And in this case, our density function is a function of x. So we can rewrite this expression as the integral over the length, and we have x by dm over the integral of the linear density function with respect to x. And now we can substitute for our linear density function and integrate from 0 to the length of the bar. And now you can evaluate these integrals and post your answer in the comments. Suppose 2 blocks sliding along a frictionless surface are attached by a string. Then we can treat this as a system and isolate it as a free body. So here we have the external forces acting on the system, and we've drawn a free body of each component in the system. And if we designate this as the total mass of the system and multiply through by m and differentiate this expression twice with respect to time, and applying Newton's second law, well, you can see that the forces internal to the system cancel out by Newton's third law. Therefore the net internal force is 0, And the mass of the system multiplied by the acceleration of the center of mass is equal to the net external force applied on the system. So here we can observe each component of the system accelerates at the same acceleration. So we can treat this as a single mass, and the net external force in the horizontal direction is F. And therefore you can solve for the acceleration of the center of mass, and then solve for the tension forces in the string using the free bodies of each component of the system. Recall Newton's second law states that the net force is equal to the instantaneous rate of change of momentum with respect to time. And the momentum of a particle or a single object with a mass m is equal to the mass multiplied by its velocity. So for a particle with a constant mass, we can write Newton's second law using the mass by the acceleration. And if we separate the variables and integrate both sides, then on the left hand side we have the impulse, and that's equal to the change in momentum of the particle, which is travelling at some initial velocity. So an example of an impulse, which is a force applied over some duration of time, is due to an explosion, which generates a shock wave that delivers high pressures to an object. So here the blast generates a very large force that acts over a very short duration on that particle. But impulses can also include collisions between soft objects where the force has a smaller magnitude and it's applied over a longer time duration. We previously derived Newton's second law for a system of particles, which states that the mass of the system multiplied by the acceleration of the center of mass is equal to the net external force acting on the system. And here we are looking in one dimension where we use the horizontal components of each force. And we found that by Newton's third law, the internal forces cancel each other out. Now if we replace the acceleration terms by the rate of change of velocity, and then multiply through by dt, then integrate the equation, we obtain the following expression. So therefore the sum of the change in momentum of each particle in the system is equal to the change in momentum of the center of mass. And that's also equal to the impulse due to the net force acting on the system. We've previously defined an impulse as the integral of a force with respect to time in the context of a particle, and that was equal to the change of the momentum of the particle. Now if we divide this equation by delta t, then by the mean value theorem, this expression is the average force. And then if we multiply through by delta t, we get the following expression. So therefore this defines an equivalent impulse where the area under the curve, given by the average force by delta t, is equal to the area under the curve of the original impulse. So in this example, where we've simplified the impulse due to an explosion as a triangular impulse, so in this case we're looking at one dimension, and the impulse is the area of that triangle. And we can also observe that the average force here is F0 plus 0 on 2, and then multiplying the average force by delta t gives us the same impulse. An explosive is detonated, and it produces an impulse on a particle weighing 1 ton, which is initially at rest, and we're asked to calculate the compressed distance in the spring, assuming no energy is dissipated. So first, using the impulse and momentum theorem, the impulse is the area under the force time curve, which is half the base of the triangle, converted to seconds, by the height, which is the force, which we convert to newtons. And this impulse is equal to the change in momentum of the particle, so because it's at rest, V0 is 0. And then once you solve for the velocity, we apply the conservation of energy, which is the kinetic energy minus the energy dissipated, which may be due to the explosion damaging the mass, is converted into elastic potential energy, and when this spring is compressed, the velocity of the mass will be 0, so the kinetic energy is 0. And then substituting the velocity from the impulse momentum equation, you can find the compressed distance of the spring. Suppose that a cue ball strikes these billiard balls, and they fly off a different velocity. And we'll take this as our system, and we neglect friction with the table, such that the net external force acting on the system is 0. So therefore the net impulse on the system is 0, and the total momentum in the system is conserved. So effectively each of these masses fly off at some initial velocity, and from this expression we can write that the initial momentum of the system is equal to the final momentum. So effectively after some time these masses will have different velocities. And similarly, the momentum of the center of mass of the system is also conserved. And recall that the internal forces to the system do not change the momentum of the center of mass, because they cancel each other out. But if we isolate a specific mass, then the momentum is not conserved for this individual mass, because you're going to have that internal impulse generated by that internal force when they interact. So for example, for a single mass, we have the following expression. We've seen that the momentum of a system of particles and its center of mass is conserved in the absence of a net external force. And given that momentum is a vector quantity, we can write the two-dimensional analogues of the conservation of momentum in Cartesian coordinates. So for example, if there's a net external force in the horizontal direction, then momentum is not conserved in the x direction, but because there's no net force in the vertical direction, then momentum in this case is conserved in the vertical direction. And you can write similar expressions for the conservation of momentum of the center of mass for the system of particles in the horizontal and vertical directions. In an elastic collision between two objects, and in the absence of a net external force, momentum in both directions is conserved. So here we have two balls colliding, for example on a horizontal tabletop, such that gravity and a normal force act in and out of the screen. So therefore, in the absence of a net external force, momentum is conserved in the horizontal and vertical directions. So if we designate our angle from the horizontal as theta, then the initial momentum of the system in the x direction can be written as follows. And that's equal to the final momentum in the horizontal direction. And we have a similar expression for the conservation of momentum in the vertical direction. And where the collision is elastic, the total kinetic energy of the system is also conserved. In an inelastic collision, momentum is conserved in a direction where there's no net external force. So here we designate our system as the bullet and the crate, and the initial momentum comes from the bullet, because the crate's initially resting in the horizontal direction. So that's equal to the final momentum of the system. So in this case, we have a perfectly inelastic collision where the bullet's lodged in the crate, and this combined mass travels at some velocity. And in an inelastic collision, the kinetic energy is not conserved. So the initial kinetic energy of the system comes from the bullet, minus the dissipated energy, which occurs where the bullet breaks the bonds in the crate to be lodged in a crate. And that's equal to the final energy of the system being the bullet and the crate. So in our inelastic collision, some of the kinetic energy is transferred into internal energy of the system. A red ball has an initial velocity, and it collides with the green ball that's initially at rest. Calculate the final velocity of both balls at the instant after impact, and verify that the energy of the system is conserved. Assume a perfectly elastic collision with both balls having the same mass. So applying a conservation of momentum in the horizontal direction, where after the collision, the velocities of the balls look something like this. And we have a similar expression for the conservation of momentum in the vertical direction, where the initial momentum in the vertical direction is 0. And to verify that the energy of the system has been conserved, this equation must be satisfied. And post your answer in the comments. A bullet has a mass of 2 grams and is launched into a block weighing half a kilo at an initial speed v0. Find the initial speed of the bullet if the block swings to a height of 0.5 meters, and assume that the bullet is lodged into the block, which is a perfectly inelastic collision. So applying the conservation of momentum in the horizontal direction, so the initial momentum of the system is equal to the final momentum of the system where the bullet is lodged into the block or crate. And this combined mass travels at some velocity. And the kinetic energy of this combined mass is as follows. And this kinetic energy is converted into gravitational potential energy. So note that if you draw the forces acting on the block, the tension force in the string is always perpendicular to the velocity of the system, and it thereby does no work. And now you can solve for the velocity of the system using what's given, and then substitute into this equation to find the initial speed of the bullet. And post your answer in the comments.